Reinforcement learning with human feedback for realistic traffic simulation seeks to develop a framework that enhances the realism of existing traffic models by incorporating human knowledge and preferences. This approach addresses the limitations of current simulation models, which often rely on simplified assumptions and lack realistic representations of human behavior. The proposed framework integrates human feedback into the reinforcement learning process, allowing the model to learn from human input and adapt to complex traffic scenarios. This is achieved through a novel human-in-the-loop feedback mechanism, where human evaluators provide ratings on the realism of simulated traffic scenarios. The ratings are then used to update the model's policy, enabling it to refine its decision-making process and generate more realistic simulations. The framework utilizes a deep reinforcement learning architecture, comprising a convolutional neural network, CNN, and a recurrent neural network, RNN. The CNN processes visual features of the traffic scene, while the RNN captures temporal dependencies and generates a policy for the simulated vehicles. The human feedback is incorporated through a feedback module, which updates the policy based on the human evaluator's ratings. Experimental results demonstrate the effectiveness of the proposed framework, with simulated traffic scenarios exhibiting increased realism and diversity compared to baseline models. The incorporation of human feedback enables the model to learn complex behaviors, such as lane changing and merging, which are critical components of realistic traffic simulations. The framework has significant implications for the development of autonomous vehicles, urban planning, and traffic management. By generating more realistic simulations, the framework can improve the safety and efficiency of autonomous vehicles, as well as inform data-driven decision-making in urban planning and traffic management. Future work includes expanding the framework to incorporate additional human feedback modalities and exploring applications in other domains. The TrafficRLHF approach is a novel three-stage method designed to enhance the realism of traffic scenarios generated by various simulation models. By leveraging human feedback, this approach aligns these models with human perception and experience. The first stage involves generating initial traffic scenarios using existing simulation models, which often lack realism due to their reliance on oversimplified assumptions and incomplete data. In the second stage, human evaluators provide feedback on the generated scenarios, identifying unrealistic or implausible events. This feedback is then used to update the simulation models, refining their parameters and improving their accuracy. The third and final stage involves resimulating the traffic scenarios using the updated models, resulting in more realistic and human-like traffic behaviors. By incorporating human feedback into the simulation process, TrafficRLHF addresses the limitations of traditional simulation models, which often failed to capture the complexities and nuances of real-world traffic dynamics. This approach has significant implications for the development of autonomous vehicles, smart traffic management systems, and other applications that rely on realistic traffic simulations. Research in generating adversarial or safety-critical scenarios for autonomous vehicle testing has led to the development of models like Strive, CTG, and TrafficGen. However, these models struggle to produce traffic scenarios that align with human perceptions of realism, highlighting a significant gap in the field. To address this, integrating human perception models into traffic scenario generation could enhance realism and improve testing efficacy. In autonomous vehicle research, developing realistic traffic models is crucial for enhancing prediction capabilities. To address this, we propose a novel approach, TrafficRLHF, which incorporates human feedback through reinforcement learning to improve traffic models. By leveraging human participation, TrafficRLHF enables the refinement of traffic models, capturing complex scenarios and edge cases that are difficult to replicate using traditional data-driven approaches. In TrafficRLHF, human feedback is used to update the traffic model's parameters, allowing it to learn from its mistakes and adapt to real-world scenarios. This is achieved through a reinforcement learning framework, where the traffic model receives rewards or penalties based on its performance, guiding the learning process. The proposed methodology consists of three primary components: a traffic simulator, a reinforcement learning algorithm, and a human feedback mechanism. The traffic simulator generates realistic traffic scenarios, while the reinforcement learning algorithm updates the traffic model's parameters based on human feedback. The human feedback mechanism collects and processes user input, providing rewards or penalties to the traffic model. Our approach demonstrates significant improvements in traffic model accuracy, particularly in scenarios involving complex interactions between vehicles, pedestrians, and road infrastructure. TrafficRLHF's ability to incorporate human feedback enables the development of more realistic and adaptable traffic models, ultimately enhancing the safety and efficiency of autonomous vehicles. The performance evaluation of traffic models is conducted on a randomly sampled subset of 100 scenes from the validation split. This includes metrics such as stability, measured by the failure rate, and realism, calculated using the Wasserstein distance between generated traffic simulations and ground truth trajectories. Recent advancements in traffic generation are highlighted, including the conditional traffic generation model, bi-level imitation learning system, and traffic gen. The authors utilize the conditional traffic generation model for traffic scenario generation and data collection. They select a subset of 500 scenes from the training split of the nuScenes dataset, process them through the CTG model, and then present the generated scenarios to labelers to determine human perception of the traffic flow. The evaluation of the reward model, and its application in fine-tuning the traffic model, CTG, is discussed in this section. The trained with 200 samples, exhibits optimal performance and is chosen for the fine-tuning process. Qualitative results, as shown in Figure 3, reveal significant improvements in realism, avoiding unrealistic collisions and off-road conditions. Quantitative results in Table 1 further support these findings, showing a decrease in failure rates associated with collisions and driving off the road. However, realism metrics tend to deteriorate when guidance is provided, suggesting potential limitations in the model's adaptability. The authors also observe an increase in variance of the RM's accuracy with increasing sample size, indicating a risk of overfitting due to the small nuScenes dataset. This highlights the need for optimizing the training process for better generalization capabilities. The qualitative results in Figure 4 demonstrate the effectiveness of fine-tuning bits and traffic gen with the reward model, in avoiding unrealistic behaviors, such as collisions and off-road conditions. The realistic behaviors are attributed to the guidance during the diffusion process in CTG, which overpowers the loss provided by the penalty losses. A performance metrics comparison in Table 2 shows that fine-tuning with leads to measurable improvements across all three metrics for both bits and traffic gen, highlighting the broad applicability of the proposed method. The generality of the learned is underscored by its ability to enhance a variety of models, including bits and traffic gen. An ablation study is conducted to delve further into the performance capabilities of the proposed method. The study involves fine-tuning the CTG model and presents the results in Table 3. The experiment explores fine-tuning specific components of the model, including the encoder and decoder portions. The results suggest that incorporating the reward model into the encoder portion leads to substantial enhancements across all performance measures, highlighting the pivotal role of human feedback in refining the model's ability to generate realistic traffic scenarios. Additionally, fine-tuning the decoder portion of the CTG model with the reward model results in further improvements, emphasizing the importance of human feedback in the decoding process. The ablation study reveals that the CTG model with full fine-tuning outperforms all other configurations, emphasizing the significance of simultaneous fine-tuning of all model components and incorporating human feedback through the reward model. The decoder or diffusing model appears more responsive to modifications, likely due to its inherent role in generating realistic traffic scenarios. Experiments on human feedback show a slight improvement in realism for the fine-tuned model, suggesting that the latent representation for the traffic model and reward model should be similar. Using different reward models also results in significant improvements on realism, indicating that reinforcement learning with human preference, RLHF, does not significantly contribute to learning better representations. This research concludes by demonstrating the value of RLHF in developing more realistic traffic models for simulation testing in autonomous vehicle development. It addresses the challenges of capturing nuanced human preferences and behaviors in traffic scenarios, ultimately enhancing the reliability and efficiency of simulation-based testing methods for future autonomous vehicles. Traffic Sim is a novel tool designed to generate realistic traffic scenarios for enhancing the safety and reliability of autonomous vehicles. It utilizes multi-agent reinforcement learning to simulate various driving behaviors and conditions, providing diverse traffic scenarios that can be used to test and improve the performance of self-driving cars. The importance of testing autonomous vehicles in diverse and challenging environments cannot be overstated, as it helps identify potential issues before deployment. Moreover, the need for comprehensive evaluation metrics beyond just miles driven without incident is highlighted, emphasizing the role of simulation-based testing in reducing costs and increasing efficiency compared to real-world testing. TrafficSim's architecture consists of three main components: a scenario generator, an environment simulator, and a reward function. The scenario generator uses a probabilistic model to create initial conditions for the simulation, while the environment simulator updates the state of the environment based on the actions taken by the agents. The reward function evaluates the desirability of the generated scenarios, guiding the optimization process towards more realistic and challenging conditions. Experiments involving both synthetic and real-world data demonstrate the effectiveness of TrafficSim in generating diverse and realistic traffic scenarios, including those that are safety-critical or involve complex interactions between multiple agents. These scenarios can be used to evaluate the performance of different autonomous vehicle systems and identify areas for improvement. In conclusion, TrafficSim offers a promising approach to enhancing the safety and reliability of autonomous vehicles by providing a flexible and efficient means of simulating diverse traffic scenarios. This tool has the potential to significantly reduce the time and resources required for testing and validating self-driving cars, ultimately accelerating their deployment on public roads. In the realm of reinforcement learning from human feedback, numerous approaches have been developed to generate realistic traffic scenarios. These methods leverage human feedback and demonstrations as a means to improve their accuracy and applicability. 15.16. One key aspect in this field is preference-based policy learning, which aims to identify a policy that maximizes a reward function closely aligned with human preferences. This approach has garnered significant attention due to its potential to enhance the efficiency and effectiveness of reinforcement learning algorithms. The authors highlight the importance of incorporating human feedback into the learning process, as it can provide valuable insights into what constitutes desirable behavior in complex environments. By leveraging this information, researchers can develop more sophisticated algorithms capable of adapting to diverse situations and preferences. Moreover, the paper emphasizes the need for more research on preference-based policy learning, particularly in terms of developing robust methodologies for eliciting and incorporating human feedback. The authors suggest that future studies should focus on creating standardized protocols for collecting and processing feedback, as well as exploring novel techniques for integrating this information into reinforcement learning frameworks. Ultimately, the integration of human feedback and preference-based policy learning holds great promise for advancing the field of reinforcement learning from human feedback. By refining our understanding of how to effectively incorporate human insights into algorithmic decision-making processes, we can create more efficient, adaptable, and user-centric systems that better align with real-world needs and preferences. This section of the research paper delves into the detailed algorithms for training and fine-tuning processes in various models, including CTG, BITS, and TrafficGen. The primary focus is on the reward model and goal conditional policy network, which are critical components in guiding traffic simulation. For CTG, the authors adopt the training and sampling procedures from 5, utilizing an encoder with a fully connected neural network that comprises hidden units of varying dimensions, 51,251,251,212,832, and a 10H activation function for all layers. The fine-tuning process involves adjusting the reward model, setting alpha equals 0.1. In BITS, the authors follow the training and sampling procedures outlined in 4. However, they only fine-tune the spatial goal network, while keeping the goal conditional policy network parameters unchanged. This decision is made to ensure a fair comparison, as the goal conditional policy network determines actions for each agent within the traffic simulation. The fine-tuning process sets alpha equals 0.5 For traffic gen, the authors adhere to the training and sampling procedures described in 16. They maintain a fixed initialization during the fine-tuning process, setting alpha equals 0.3. All fine-tuning processes employ an amended PPO from Colossal AI, 30, as their fine-tuning strategy with 70 epochs. The traffic simulation is performed using a standard control loop, where the model generates a guided trajectory and executes the initial few actions before replanning at a set frequency. In all experiments, each scene is rolled out for 10 seconds, starting from a ground truth driving log and replanned at a frequency of 2 Hz.